All right. Good morning. My name is Mitsuhiro Shibayama. I'm a director of the Neutron Science and Technology Center of Comprehensive Research Organization for Science and Society. We call it CROSS. And first of all, I'd like to express my deep thanks to the organizer, particularly the Sergey, for inviting me to such a great conference. This is I believe, the sixth Polymer conference. Okay, so the title of my talk today is Dynamic Light Scattering of Polymer Gels. All right, so this is the contents of my presentation. Starting with the introductions, I think many of you may be aware of these stories, but let me repeat it as a general introduction. And then it is followed by some topics about dynamic light scattering polymer gels. And then the last part, I'll give a talk about recent advancement of the achievement of our groups of these kind of topics. Okay, so what is the colloids and colloid science light scattering? I think you may know all of the story, but let me repeat. The Brownian motion was discovered by the Robert Brown in 1827, and then Albert Einstein to explain or predict the theory of a Brown motion, and a few years later, Jean Perrin proved the Brownian motion experimentally. So this is the colloid science. On the other hand, light scattering started by Lord Rayleigh, for example, and then he proposed the scattering theory. And later on, Peter Debye applied it for the polymer characterization. This is a kind of good combination of the colloid science and light scattering. So this is the history of the light scattering. Again, the Rayleigh started the theory with the scattering theory for the small particles whose size is much smaller than the wavelength of the light. And then it is famous saying, which is given by the Rayleigh, blue sky, the red sunset, and this is the Rayleigh's force power law. And also the Rayleigh proposed the theory for the spherical particle with arbitrary sizes, with the refractive is very close to the unity. And then the Debye extended the theory for the macromolecules. On the other hand, me proposed the theory with me scattering. It's with the large particles where the refractive index is much larger than the unity. And fluctuation theory was by Minkowski and Einstein, the scattering theory for the condensed system and density and or concentration fluctuations. And you may know the critical scattering as well by the Zernicke and Prince, and then scattering from particles with spatial correlations and near the critical operations, critical divergences. And also polymer characterization was developed by Debye and Zinn, which is the combination of Rayleigh-Debye theory plus thermodynamics. So this is the kind of beginning of the polymer solution characterization, and then we could obtain the molecular weight, molecular size, conformation, interaction parameter, and such and such. So this cartoon is the slide of my introductory talk. You can see some Chinese or Japanese letter here. This is photon, and it's the photons coming into the sample, which is, for example, the gel, and then photons are scattered by the gel and then received by the detector. So if we plot collect the scattering photons as a function of the scattering angle, so this is the static scattering. On the other hand, by fixing the detector position and then just collect the photons as a function of time or time interval, it is called the dynamic scattering. So this is the static scattering and dynamic scattering. We can both obtain the information about the structure and also the dynamics. This is another aspect of the static light scattering and dynamic light scattering. So in the case of the static light scattering, the particle is in a rest, and then it generates the spherical wave from the particles. Then by getting the interference to the two particles, blue and red, and then we can get the structural information by the interference. of the two waves. On the other hand, if the particles are in motion, so we have two ways to study the dynamics. One is the spectroscopy. By frequency change, we can get some information of how fast the particles are moving. On the other hand, the other one is the time correlation. By taking blue and red, the time differences and how we get some information about the dynamics, which is called the time correlation, photon correlation spectroscopy. So the principles and characteristics of the dynamic light scattering, the origin is the density and or concentration fluctuation in the matter via refractive index and fluctuation in the scattering intensity from Brownian particles. What we measure is time correlation of the light scattering intensity. The information we can get is the dynamics, such as motion and regulation of the matter via relaxation rate. This photograph showed how the laser pointer beam is scattered. This is milk. If we can use the regular milk, we cannot get any information because it's too opaque. So by dilution 10 times, 100 times, and 1,000 times, now we can see the trace of the laser beam, and from which we can get some information about the dynamics. So this is dynamic light scattering. The characteristic of dynamic light scattering are the non-contact measurement, high sensitivity, high precision, large range of the object size, such as from angstrom order to a few tens micrometers order. And then this is another important point. Only two parameters are necessary. One is the refractive index and the viscosity of the medium. So systems suitable for dynamic light scatterings are shown here, such as particles and colloids and fine ceramics, magnetic tape powder, toner, pigment, and such and such. There are a wide range of the sizes, as I mentioned in the previous slide. And then this is complementary to other techniques like laser diffraction, electron microscope, and optical microscope, and such and such. Then the system we observe the dispersion, such as colloids and surfactants, and where we can obtain some information about size distribution. And then polymer solution, we can get size of the polymers and distribution, aggregation, etc. And then system is the distributions and dynamics of the dense system. In particular, the case of geos, we can obtain some information about correlation lengths and inhomogeneities and gel points. Okay, so much for the introduction. Let me move to one of the main parts of which is dynamic light scattering of polymer gel. Here, I'm discussing about the Tanaka-Hoka-Benedict theory, specular non-ergodicity, gel point determination, and dynamic static decomposition, inhomogeneities in polymer gels, and probe diffusions. So this shows the Tanaka-Hoka-Benedict theory. So Tanaka at the MIT developed the theory, which is the continuum equation for the dynamics of the polymer gel. As a matter of fact, he treated the polymer gel as a string of the polymer chain. And then this shows the displacement vector, and the sigma is the stress tensor. So starting by this equation, this is the inertia term, this is the force term, and then he developed the theory. But before I'm going to the theory, let me show the examples. One is the diffusion of the dye molecules in ink, and the other one is the swelling of a gel. So in the case of diffusion of dye molecules in ink, each ink pigments diffuse independently. This is why, starting from the rectangular shape, this ends up the round shape, as you see here, or you can have some experience by yourself. On the other hand, in the case of swelling of the gel, the gel keeps its own shape. Why it happens? The reason is that each polymer chains are connected to the neighbors. So this is why they have to minimize those stress or strains to keep the shape. This is the essential point of the swelling of the gel or diffusion of the gel. So starting from this equation, he manipulated this term and expanded this to this. And then by ignoring this term, inertia time, he simplified the equation and end up the diffusion equation. This is well known, the diffusion equation, where the UI is the displacement vector, or just displacement, or the direction of E, X, Y, or Z. So if the electric field is applied in the z direction, and then we can have two diffusion coefficients. One is the longitudinal diffusion or the transverse diffusion. So the factor are a little bit different from each other, where the K is the bulk modulus, G is the shear modulus, F is the friction factor. So now he tried to relate to the displacement with the displaced electric field of the light. The time correlation function of the electric field is given by this equation, which is proportional to the displacement correlations, and then it is proportional to the single exponential function, where gamma is the relaxation rate in the case of Brownian motion. Then what we observed is not electric field, but the scattering intensity. This is why we usually obtain G2, and which is kind of the square of the G1. And then this is why factor 2 comes in because of 2. And then the gamma is diffusion coefficient D is related to the correlation length via Stokes-Einstein equation, and which is analog, more or less the parameter of the mesh size of the polymer chain. And he also, those people, Tanaka, Hoka, Benedict, did the experiment, macroscopic experiment of the friction measurement. They set it up this kind of system where the water is in here, gel is here, and then by the gravimetric force, the water goes through to the gel, and then by measuring the time rate of the water flow, they obtain the friction factor F. So this is a plot of the one diffusion coefficient obtained by microscopic method, which is deep light scattering, and also the macroscopic diffusion coefficient obtained from this equation. And then, very interestingly, both are very good in agreement. So this is the case of polyacrylamide 5%, and then this time temperature up, temperature lower. So it's a somewhat reversible. In good agreement between the macroscopic measurement and microscopic measurement. So this is a proof of the theory of the Tanaka's. So just after that, so the Tanaka's group found some speckles in scattering from the gel. So this Michael Orkis, I was with him at the 1991 at the Tanaka's lab. What was interesting was this is a microscope setup. Here the fibers, and then this is a fiber to the correlators, and then we can observe what is happening under the microscope. And this is a trace of the laser beam, and then we can have a lot of particles brightening, and we can see the trace. This is regular light scattering, and then this is the polystyrene latex. Remember that I showed the milk. This is now the polystyrene latex, the 54 nanometers per thin particles. If we replace this medium to the gel, something different happens. As you see here, a lot of speckles appear, as you see under the microscope. More interesting, what was happening was, so when we open the aperture, the speckle pattern becomes very narrow, sharp, and then by minimizing aperture, the speckle becomes larger. So this clearly indicates this is not the time spatial variation of the concentration fluctuation. This comes from not the interference of scalar light, and not to the some intrinsic length scale within the gel. So this is important part. So this is a result of the reflection or diffraction pattern. Speckles are due to an interference of scalar light and not to some interesting length scale within the gel. So before that, the Buzzi and Van Wegen discussed the non-ergodicity of the gel together with the speckles. So this is a famous cartoon described by them. So this is a comparison of the solution and gel, and so there's a non-equality between the ensemble average and time average. In the case of a solution or dispersion, whatever, time average is already this equal to the ensemble average. This is ergodic assumption. However, in the glasses, it's completely different because in glasses, nothing is moving, so the time average is not the ensemble average. But gel is very interesting. Those are gels are in between to the solution and glasses. So as a matter of fact, we did a similar study to follow them. And then this is the polymer solution without crosslinker. This is the polymer gel with crosslinker. So in here, the ensemble average is the same as the time average. However, in the gel, you see the very vigorous variation of the scatter intensity, and each red point represents the time average because we're measuring the intensity by taking time average. But the ensemble average, by definition, we can take all of the time average over the positions. So this is ensemble average. Definitely, those are different, are not the same. So then, what's the reason of the speckles? So this is my understanding. Dynamic light scattering colloids and versus gels. In the case of colloids, for example, there are moving particles that undergoing Brownian motion, and then the transverse coherence length. This is laser beam, and coming into the samples. And then each particles are moving independently. This is why the response is just independent each other. However, what is happening in the polymer gel, if the wavelength is smaller than the transverse coherent length, and then larger than the mesh size, what is happening is that there is interference between the two, some interference between the two. So as a matter of fact, this correlation function is not this, but like this, which is a combination of the homodyne component and heterodyne component, and the ratio of the two is given by x p. So this is corporal diffusion, and p stands at the position, so x p depends on the position of the scatterer. The corporal diffusion can be obtained by these equations. The correlation length of mesh size is obtained more or less. So then the Johnston in 1991 proposed the partial heterodyne theory. So again, this is the equation they proposed, and they obtained this kind of statistics. The population of the scattering intensity, which gives the I sub t, is this kind of function, the decay function with a lower bound. So this is the lower bound. This is the fluctuating component of the system. And then those points are coming from the heterodyne part. So dynamic fluctuations, if the two beams are coming into the samples and both are moving, if the both are moving, you have the single exponential decay times single exponential decay. This is why we have two doubles of the decay function. But if one stop at the fixed point, like a local oscillator or a mirror, then there's no decay. It ends up with the heterodyne mode. So this is a kind of very clear or easy to understand what is happening of the heterodyne and homodyne. So, but to decompose the heterodyne and homodyne is rather difficult because it's just a factor of two. So let's say to just fit with a single exponential function with apparent diffusion coefficient dA, which is dependent on the position. So by measuring the apparent diffusion coefficient, we can learn something else. And also initial amplitude is defined by this one. So then we proposed a very interesting or useful method to decompose static and dynamic contributions. So first we obtained scatter intensity by scanning the sample positions, and at each point we measure the time correlation function here and here. So then we can sort or rearrange the scatter intensity of the apparent diffusion coefficient as a function of the scatter intensity. We get this one. This is exactly the same as the Johnston's results. So then by rearranging the previous equations to this form, I think as a matter of this, So now we can get the, this is the slope. Excuse me, this is the slope, and this is the intensity here. And then from the slope, we can extract the diffusion coefficient, and from the intercept here, we can extract the fluctuating component of the scalar intensity. And also from the ensemble average, we obtained the ensemble average scalar intensity. So each three of the important the parameters for the gel scattering can be obtained by this plot. I'm happy to have this kind of plot. I'm showing this another option in the later discussions. Another aspect of the gels is the distribution. As you know, the inverse Laplace transform, which is often called content analysis, is very useful for the dynamic light scattering. So advanced version of the cumulant analysis is given by this equation, and the correlation function is just a Fourier Laplace transform of the distribution function. So by measuring correlation function and take an inverse Laplace transform, in this particular case, content, we get the distribution function. Okay, so what is happening in the polymer gel? This is the Tanaka-Hoka-Benedict theory, and this is a single exponential, and what we expected is a very fine curve or distribution. This is the case with developed gel, and this is the prediction by Tanaka. However, what is happening if we have a very unmatured gel? This is just above the solid gel transition. In this particular case, the gel dynamics is far from this kind of single exponential. What is happening is a very broad distribution and unmatured gel. But by simply observing this, it is very difficult to predict, to guess how broad this distribution is. But on the other hand, by taking the inverse Laplace transform, content analysis is very clear. It has a very broad distribution of the many magnitude of the time order. So this is one example for applying for the milk. There is various kinds of milk having a low fat to the high fat, high content of fat. Again, here it's very difficult, which is sharper, which is broader. But by taking the transform, inverse Laplace transform, it is very clear how broad the distribution is. This is simply application. So coming to the gel point determination by light scattering. So it was an interesting paper by James Martin in 1988. He did the real-time observation of the scalar intensity, dynamic light scattering intensity as a function of gelling time. And he obtained this one. And then he observed at the gel point, it becomes a power law. And then dP is the fractal dimension of the scalar photon. So by getting this kind of the idea, we did a similar thing. And then my colleague Norisuye did the experiment, which is the polymer gelation process, starting from monomer solution, and then watch what is happening at just observing the scalar intensity. And what I was surprised was there's nothing at the beginning, but here there's very spike-like scalar intensity rise, followed by some fluctuation, but which is much lower than that. So at the beginning, we thought this is just a mistake, but what is happening, it is not, because at the beginning, the particle is so small, it doesn't scatter so much, but here, the polymer chain becomes grow and grow and occupy the whole space. So this is why the scalar is very big. This is why the strong scattering. However, from here to here, this is now it's a condensed matter. It's continuum. This is why there's no envelope. So this is why scalar intensity decreases. This is analogous to the vapor liquid transition. You see the critical opacitance of the gases. This is the same case. So by using this technique, we extended gel point determination of the gelatin by dynamic light scattering. Here's the gelatin gel, and then with cooling process, and we did a data measurement from the 40 degrees of centigrade to the above 10 degrees. And then this shows the scalar intensity change as a function of time, and also the correlation function change as a function of the time. So what we found is increase in the scalar intensity, abruptly scalar intensity at the gelling point, and also the time independent, also depression of the intercept, initial amplitude. So time independent, the corrosion component becomes large by some system freezing. So this is the way how to measure the zero point. And then concurrently, since we are working on the gelatin, it is easy to obtain the rheological results. And we did compare the same cases. And then this is more or less the experimental error, the rheological change, and also corresponding with the scattering changes. So the question is solid transition is unique for the speckles, or if we observe speckles, it does correspond to it means the solid transition. And we did some cases, which is the polyvinyl alcohol conglomerate. This is the conglomerate molecules. And in the case of polyvinyl conglomerate, there is some hydrogen bonding, and then it undergoes solid transition. So what's more interesting was it undergoes solid gel transition simply by changing conglomerate concentration. A conglomerate concentration 1 millimolar, it's a sol, and 4 millimolar, it's gel, and further increase in the concentration becomes a gel, as you see the meniscus. So regarding the concentration dependence, you see the speckles exclusively appear in the gel state. And also the time temperature dependence, since this is a time reversible phenomena, we increase the temperature and then gel to solid transition occurs, as you see here, and vice versa. So, and also in the gel state, we have a power law behavior, and solid state, we have a stretch exponential. So far, the speckle is the good signal of the solid gel transition. So then we propose the inhomogeneity in polymer gels. So the polymer solution, there's Brownian motions undergoing, but in the case of gel, which has, in addition, we have a cross-linking inhomogeneity. So there are several ways of characterizing this inhomogeneity, such as spatial inhomogeneity, topological inhomogeneity, connectivity inhomogeneity, mobility inhomogeneity. Those are more or less independently observed by different methods, such as static scattering like X-ray or neutron, and then the sweating experiment or modular experiment, or some of the dynamic light scattering or speckle. Okay, so now let me move to the probe diffusion analysis of polymer gel. So since the polymer gel is a very interesting system, but at this time, I don't have a very good correlators. Scattering setup. Laser beam is only 5 milliwatt. So then we decided to put the probe like a polystyrene latex. And this is the case without latex and with latex. And this is the blue one is without latex, and we observe corrective diffusion. But in the probe diffusion, we see the corrective diffusion. And then we increase the cross-linker concentration from 0, it's a polymer solution, to the polymer gel. And then, so this is a correlation function. They show the distribution function. This is more interesting. Here, it survives without, irrespective of the cross-linker concentration, but the probe diffusion, like starting particles, get slower and then they disappear. So this means because of the cross-linking, the polymer probes cannot move. So the distribution function analysis, in a sense, is much more sensitive or superior to the correlation length analysis, correlation function analysis. Only corrective diffusion observed at high cross-linker concentration. Okay, I think I have to finish in 1 hour, so let me just rush up. So recent advancement, and this is some interesting story coming here. The first I showed the dynamic light scattering microscopy. At the beginning, I showed we need to dilute the sample, which have to transparent or very highly transparent to obtain the intensity. So my colleague Hiroi developed a new method, which is microscope. So this is the setup. We're using argon laser, and we have a confocal, fast confocal, and it goes into the sample, which is inverted microscope, and then the photon intensity of information comes back from this sample position, and then goes by going through the half mirror to the autocorrelator. So this confocal setup, this is all we can change the depth of the samples. And then those are published in this paper, or also the Journal of Visible Experiment. You can visit this one as well. So let me show the result. There are two cases. One is polystyrene beads. Remember, in the case of milk, it was opaque. This is a case of polystyrene, and in about 10% or 1% of polystyrene beads. So we cannot get any information from the dynamic light scattering, but this is why we need to dilute, such as here, the dotted line. This is a conventional dynamic light scattering, but this method, dynamic light scattering microscope, can allow us to obtain this kind of distribution without dilution. Same thing happening in India. It's a completely black. This is not multiple scattering. This is just absorption. And conventional dynamic light scattering, we need to dilute about 100 or 1,000 times. However, the iris microscope allow us to obtain this kind of size and also distribution. This is a unique feature of that. So this is topic one. The second one, the isorefractive index probe diffusion. So isorefractive index probe diffusion analysis. So we are successful to measure the polymer diffusion and particle diffusion in this particular case, water, polymer, and polystyrene beads. This is okay. We can get the dynamics of the both components. However, if we focus on the particles and what is happening in the matrix of the gel network, so we try to remove this contribution. So what we chose was this combination, DIMSO and PEG. The refractive indexes are very close to each other. Then by using gold particles instead of polystyrene, and then, so this is the result. One is a non-isorefractive PEG acetonitrile solution. We have two contributions, collective and probe diffusion. Then this is an isorefractive case. There's nothing coming from the collective diffusion. We can just focus on this, the probe diffusion. So what's the merit of this method? Which is as follows: this comparison of ideal and random network gel. This is ideal network, and then we change the probe particles from the 57 to the 28 nanometers, and we apply this kind of equation from which we can obtain the amplitude and then characteristic time, and also the stretched exponential beta. And then irrespective of the gel particle size, this is almost more or less the same. Well, however, in the case of random network, it depends on the particle probe sizes. If the particle is large, it's narrow, and then when we decrease the size, it becomes broader. What does this mean? So this is a message. So if the end cross-linking well-developed gel, and then there's a very sharp transition occurs from solid gel transition, but if the random copolymer gel, because the network itself is very broad distributions, this is the why it depends on the size of the particles. Okay, now let me move to another system with a speckle-free gel. So far, we have a long history, but the gel is inhomogeneous. It is inevitable to remove the cross-linking heterogeneity. So my colleague Shan Li tried to remove of these heterogeneities with the many strategies. There are two cases. It is high concentration, low concentration, and high concentration, there's a dense region. So with some inhomogeneity because high cross-linked part of the fast connected part, and also the aggregation may occur. On the other hand, sparse regions, because of lack of the polymers or cross-linkers, it has a voice or nanobubble. So try to remove all of these causes. We did start with the star macromolar, and then good solvent, and also concentrated solution. Try to fill all the spaces, and then by nanobubbles can be removed by nanofilters. Okay, so then this is how we made the ideal gel. Starting from star macromolecule, which is we call the tetrapeg gel or 4-amide gel, and then it undergoes cross-linking at the ends, and then the cross-linkers, and then the concentrated solution to fill all the spaces, and also good solvent. Remember, in the case of water, there are two shoulders. This is the gel mode, and this is a translational mode or some vacants or the heterogeneities. But by using acetonitrile, acetone is a single exponential. So we can remove, this is a good solvent case, we can remove the aggregates. And also nanofilters, and we can remove all of the bubbles, then at the end up to the very clear gel. So this is the evidence of the speckle-free gel. This is a setup. An inverted microscope, the laser beam is coming through this one, and please take a look. This is a conventional gel starting from the monomer solutions, nothing happening at the beginning because the monomer solution, and somewhere here, you can see some speckle appears at the gel point. Now speckle is coming, and duration occurs. To save the time, I just go faster. Okay, so at the gel point, and we can see the speckle. So now that this is a comparison of the gelatin of the macromonomer solution. This is ideal gel, speckle-free gel, and this is the same one as shown in the previous slide, the conventional gel, starting from monomer. But in this case, from the very beginning, it was a polymer. This is a polymer solution undergoes polymer gel because by connecting. So this is why at the beginning there's strong scattering, but this is nothing. So please take a look carefully. Now in the solid state, and then the solid state, and now gel state and gel state. I think you didn't watch here carefully, so let me repeat. In solid state and gel state, nothing happening. So the speckle is no matter this is not the indication of the gelation. So I'm happy, and I'm also unhappy of this result. But I don't think you believe my results because we do not know the real gels. So now we did a viscoelasticity measurement. The upper one is dynamic light scattering experiment. The bottom one is the dynamic viscoelasticity measurement. If it becomes a gel, the G prime and double prime change a lot. So take a look again. Here, the G prime and double prime now is increasing, and then solid gel transition occurs, but here it's nothing happening. So through the solid gel transition, correlation length doesn't change, but it does change a lot. So of course, at the beginning it's flowing, but at the end it doesn't flow. Okay. So by knowing this, that we extended experiment by fabrication of to fabricate the three types of gel: lower doped, over doped. So ideal condition is under a bond percolation. We fill the space by monomer, macromer, and then just let it cross-link together, then end up to the homogeneous gel. However, we decrease the monomer macromer concentration, now it ends up to the gel, but it's some sparse region. This is the site percolation. And on the other hand, if we add more macromer at the beginning and let the gel and then have aggregate. So it's analogous to the semiconductor. It's a hole type and overdope type. So then this shows the comparison of the viscoelastic behavior and the speckles and such. And then also we did a Sachs experiment of the three systems: ideal, hole type, P type, and N type. As you see here, the bond percolation, ideal gel is the lowest intensity, it is homogeneous. But in the green one, it's P type, it becomes larger. And then overdoped one is more heterogeneous than the others. So we can estimate the correlation length and then some radius of gyration if there are some aggregates. So we can obtain all of the information from this. And also time average versus ensemble average. So there are two averages, remember? So time average and ensemble averages. And the solution, it doesn't change. Those are identical, but there is the different. So this is the equation how to obtain the ensemble average correlation function. Starting from time average correlation function, we need to measure many points and then take the average. So this one is ideal gel and time this is ideal gel correlation is all the same from the solid state to gel state. Remember the macromer solution and macromer gels. And then ensemble average, even the macromer, it doesn't change at all. Time average, ensemble average, this is exactly similar to the ideal gel. However, in the case of conventional gel, it is different from the solid state, and then at the solid gel transition, it becomes suppressed, and then even more suppressed by that. And the ensemble average completely different from that of the ideal gel, as we predicted, or the Pussy name predicted. So now this is some summary of this kind of static dynamic decomposition of the three types of gel. Remember, I showed we proposed the static dynamic decomposition method. In the ideal case, there is no distribution, just a single point, and p type some broadness appearing, and conventional type or this overdose type has a wide distribution of the correlation length and such and such. So again, we can do the same thing by using this plot. Okay, let me go to the final topic, jamming transition of microgel. So colloids. The colloids are ubiquitous. You can find milk, ice cream, paint. There are lots of colloids. So what's the difference between the gels and colloids? Colloids is ergodic medium, and then hydrostatic radius is very wide in range. And gel is no ergodic media. I have discussing so far. And then this is a microsphere gel speckle patterns. So what happens in microgel? So we can decrease the size of the gels, and it can be microgel. Again, the colloids and gels are much, there are differences. High diffusivity and soft and easy to handle, steam responsive, high specific surface area, and such and such. But now the question is, dense microgel, what is happening? They call the taste. And then this is some result by report by rheology. Urayama and the Kyoto Institute of Technology, now he's in Kyoto University, he did some measurement of the rheological measurement. So by measuring the stress amplitude and strain amplitude and the G prime, double prime, he obtained the elastic plastic transition. So at low shear rate, this behaves as elastic matter, but by shearing with the increasing amplitude, it starts to flow. So this is plastic transition. This is one of the methods to determine the time jamming transition or something. So similar one was done by dense microgel based by diffusive wave spectroscopy. So by measuring these parameters, and then we can they can obtain some information about the pace dynamics. However, what is happening by dynamic light scattering is multiple scattering, and it becomes opaque. So this is why dynamic scattering has been believed to not be applicable for this kind of system. So we try to remove this kind of problem. So dense microscope paste by DLS. So this is dynamic light scattering of non-opaque gel paste. So what the key point is, we chose the very small sizes of the nanogel, which is about a few tenths of nanometers, which is much smaller than the wavelengths of the light. So starting from the low concentration, high concentration, this is a plot of transmittance, which is somewhere here. And then this is ride rate, this is a C-star concentration, this is a chain of particle override concentration is somewhere here. And then override is more than 100%, 800%. And then the multiple scattering is negligible because it's transparent through the whole concentration range. So by using this system, we did the dynamic light scattering. So now we can classify three regions. One is dilute, and the intermediate are dense. The dilute region is a single exponential, and in intermediate region we have a slow mode, and then up to here, then suddenly it goes down to the green, red one, dense region. So it moves like this way and then this way. So then let me discuss one by one. So dilute region is a single exponential from which we can easily obtain the diffusion coefficient or hydrodynamic radius, which is exactly what we expected because we know the size of the particles. So then intermediate, it is something different. Now slow mode appears, and it is fitted by stretch exponential. And what is happening is that there are two modes, fast and slow mode. And fast mode is let me discuss fast and the slow mode. Slow mode is the decreasing function of the concentration because the slow mode, the ability becomes slower at increasing concentration, which we can expect that. On the other hand, fast mode is very interesting. Fast mode becomes faster by increasing concentration. So this is, since it's just gel mode, this is why by increasing concentration, the diffusion coefficient for the it becomes faster. Then anyway, fast mode is here, and then it's the increasing function of the concentration, and then even more higher at the stage 3. So the translational diffusion and corrective diffusion. So how about the concentrated region? Region 3, again, in this particular case, static phase and floating part is dominant. And remember, this is gel, the time average is non-ergodic. So now we compare this with the static light scattering. So at the diode region, the scattering function can be fitted by spherical form factors, so which gives the radius of the particle. But the intermediate region, we still have some decay of the function, which means the sphere form factor is still alive. However, further increase in the concentration, now form factor disappears and duration of jamming transition occurs. Now, summing up the discussion so far, the dynamic microgel starting from dilute and single exponential, intermediate, slow, and fast. And dense part is very non-ergodic, and that's the ensemble average static equation. This is the case where we have here, right? So now, can more summarize what is happening, the dynamics of microgel, and then the dilute region, intermediate, and concentrated region. All of the light concentrated regions, we can use the light scattering owing to the transparent nanogel paste. So the DLS allows to determine the volume-free concentration system, a jamming transition C-jam, somewhere here, of the gel. So different behavior from so-called hard colloids. This is a message, take-home message. The difference from the hard gel are large intermediate concentration region and the presence of gel mode even above C star, and due to the soft and deformable nature of the microgel. So this appeared in the paper. So summary, the jamming transition is characterized by the ensemble average of the correlation function. The jamming transition is very clearly found by this equation. DLS allows to determine the volume filling and the jamming transition of the microgel. So concluding remarks on viscous scattering methods, characterize the structure and dynamics of source matter and demonstrate particularly by emphasizing the relationship between structure and rheological properties. And topics in my presentation were jelly homogeneity, decomposition of static dynamic components, and solid transition point determination by light scattering, and probe diffusion and DLS microscope, speckle-free gel, dynamic microgel over the wide range of the concentrations. So at the end, let me conclude my presentation by showing this one, a relationship of colloid gel classes. Since we are polymer scientists, we usually start from the monomers, and there are many systems such as gels, colloid, glasses. So if we polymerize the monomers with the cross-linkers, we have gelatin gas, and then if we polymerize the monomers with the surfactant monomers, and then we have colloids, and then if we polymerize with a solvent, we have a vitrification occurs and some vitrification transition occurs. So it's a solid gel transition, a glass transition, and all of this solid gel transition, jamming transition, all of these can be handled by the polymer system. It is nice of the polymer science. So some of this was in this article, Soft Matter, this year. And I thank you very much for, excuse me. First of all, those are papers related one. I didn't have a time to graph transition, but it appeared in the polymer about 20 years ago, and the translation diffusion and PRL for the solid gel transition. And then at the very end, I'd like to acknowledge to my colleague and the supervisor, Toyo Tanaka, at MIT, when I would stay there for 1 year. And the time I learned light scattering. Before that, I did a small angle X-ray and neutron X-ray, but not the dynamic light scattering. So this was my beginning of the dynamic light scattering research. And then coming back to the Japan, I was at Kyoto Institute of Technology. I worked with the Norisue and he did the gel point determination and decomposition. And after moving to the University of Tokyo, we have good coworkers, Hiroi of the DS microscopy, and then spectrophysiology with Shanli, and then microgel jamming transition with Kureha. Thank you very much for your kind attention. I'm happy